Hello everybody, welcome back to another Civi 398 example tutorial. In this tutorial we're going to be covering our second ABAQUS tutorial, which deals with a cantilever beam but with a hole in the middle of the beam. So last time we dealt with the cantilever beam, we're going to analyze the exact same model this time, except we're going to add a hole into the middle of the beam, which is great because of course in your guys' assignment, you guys have a wall with a hole in the middle of the wall. So what you guys should take from this video is how to create a hole inside of your guys' parts, which it sounds really funny, but it's something very valuable to know when we're dealing with ABAQUS. Alrighty guys, so if we look at our beam, as we can see, we have the exact same scenario that we did in example number 1. The only difference is we have a hole in the geometric center of our beam with a diameter of 0.125 meters. Everything else, from the material properties to the geometric properties to the loading scenario, remains the exact same. So from this, we can go into ABAQUS and simply solve this beam. Now, unlike the first tutorial, I'm actually going to go a little bit faster and not go into as much detail with a lot of these things because we did that back in the first example. So if you guys are saying, you know what, Clayton, you're going a little bit too fast for me, well, I highly recommend you guys go back to example number 1 or check out example number 1 if you guys haven't, because since that I assumed being your first ABAQUS tutorial, I took things quite slow and really explained all of the steps more in depth. This time I am assuming that you guys are a little bit more familiar with ABAQUS, you know what we're doing, so I picked up the pace a little bit to hopefully save you guys some time. Alright guys, with that being said, let's jump into ABAQUS. Alrighty guys, so as I mentioned, we discussed a lot of the nitty-gritty things in our first example videos, so this one, we're not going to go into as much detail when we're talking about the basic things, but if there's something that I didn't talk about last video that I think needs highlighting, of course I am going to do that in this video. Alright, so we're going to follow the exact same process as the last video because it really showed how we create models in ABAQUS and how we run them. And as you guys will see, that same process really applies to any model. The only difference is if your model is a little bit more complex, you guys might spend a little bit more time in each one of the modules. All right, so the first thing that we do, of course, is we want to create our part. So if we look up at the top here, I am in the part module, and I can create my part one of two ways. The first way is I can click the button here that says create part, or I can just simply double click on parts. So I'm going to double click here, and it's going to want a couple of inputs. The first one is the name. Well, I know that I'm creating a beam, so I'm just going to call this my beam. Again, the second thing it's asking, is it 3D, is it 2D, or is it axisymmetric? Of course, we don't deal with 3D in this course. We haven't talked about axisymmetric. We know that we just want a simple 2D beam, so I'm going to click that. And then down here, I can go continue. Now, one thing that I want to show you guys now, since you guys have already seen the ABAQUS part creation, is this approximate size. So as you guys remember last time when we started drawing our part, we were given grid lines. Now, the size of those grid lines is actually has to do with this. If I were to make this really, really big, I would have the grid lines extend much further. Remember in the last video, once we zoomed out, our grid lines were actually only a very specific part of the model. But if I put the approximate size to something really large, I will have much more grid lines. So I'm going to go continue. And it's saying that, you know what, Clayton, that's a little bit too big. Let's put it a little bit smaller. So now when I zoom out, this is actually much more grid lines than I had before. All right, even though it doesn't quite look like it. So what we're going to do is we're going to create our beam the same way that we did before using this nice create rectangle function over here, and it wants 2 points. So what I'm going to do is I'm going to say that my beam starts at the bottom left corner at the origin. So I'm going to enter 0, 0, and as we can see down here, it entered 0, 0, and I'm going to click enter. So of course I have that point, and then I want to specify the point of the beam all the way on the top right corner, which we know occurs at 2000, because again, I'm doing things in millimeters, and it has a height of 250 millimeters, so I'm going to go 2000, 250. We can see it down here, and when I click enter, it creates my beam. Now, this actually emphasizes what I was talking about with the grid lines, because remember before, once we zoomed out, our beam actually came all the way over here, but now we see that since we added the approximate size to be much larger, the grid lines actually encompass much more of the shape than they did before. But again, this plays no impact. If my shape is all the way out here, it doesn't matter. ABAQUS doesn't really care. So the next thing that we have to do that we didn't do last time is actually create the hole in the beam. Last time we just had the beam, but now we actually have a hole in our beam. Luckily for us, ABAQUS gives us a bunch of options to draw a bunch of different shapes, but since our hole is a perfect circle, I can go to create circle over here. So I'm going to click it, and it's going to say, all right, where is the circle located? Where is the center of the circle located? And we know that this is at the geometric center of our beam. So half of the length of the beam, well, that's going to be 1,000. So I go 1,000 for X. And of course, half the height of the beam is 125, not 150, 125. So I go 1,000, 125, I click enter. And as we can see, the center of our circle is right at the middle of the beam. So now it says, all right, you need to pick another point to kind of specify how big this radius is. Now, we have to enter in a point. We don't just type in what the radius of the circle is. So what I'm going to do is I'm going to do the point to the left of the center over here. So all I need to do is go half of the length of the beam minus the radius. So I get 875. And then, of course, it's located at the same height because I'm just going laterally. So this will still be 125. So I enter that. I see that my circle is way too big. But this is just fine because what we actually did was we entered the diameter of the beam instead of the circle. Now I did this on purpose because this is something I want to show you guys, which is this. Let's say that we enter something and we actually mess up a dimension. Well, we can actually specify the dimension. So we can specify the dimension here, and then we can go new dimension down here. We said, oh, we entered 125. That was actually the diameter. The radius, of course, is half of 125. So I'm just going to go 125 divided by 2. As you guys will see, it'll automatically adjust. Let's say that I still entered the wrong one. I have a button over here that says edit dimension value, so I can click that. I can click this again, and it says, all right, well, you messed up again. What do you want it for the third time? Let's say I want it 85. I can go apply, and as we can see, it always keeps changing. But of course, we know that we want it as half of the 125. So we specify that, we are good to go, and now we have our circle in the middle of the beam, which is perfect for us because now that we have our beam defined, we can simply click done, and we have our part right here. So we have our beam, has the hole in the center, we are good to go. So now we can move on to the next module. So I click down, and the next one is properties. So this is where I start assigning material properties to this beam, because right now it's just a shape, it's nothing too special. So I can come over here and do this create material button, or I can go down to the model tree and double click on materials. It'll give you the same menu. So just like before, we have an elastic material, so I'm just going to name it elastic, and we know that we can find the elastic option under mechanical and then elasticity. So I'm going to come over here. We're going to click on elastic, and it wants two things, which is expected. The first one is the Young's modulus, which we know is 20,000 MPa, and the second one is the Poisson's ratio, new, which we know is 0.2. So enter those in, I click OK, and as we can see, we now have a new material property defined under materials. So the next step before we move on, of course, is saying, all right, I have my shape, I know it's elastic, therefore I need to specify that this shape is elastic. So in order to do that, we can go assign section, and it's going to say, all right, well, which part do you want to assign the section to? Well, we know we want to assign it to our shape over here, so I'm just going to highlight it. I'm going to click done, and it comes over here and says, what section do you want to assign? So again, we haven't created any sections yet, so we can click the button on the side here that says create section. I'm going to do that, and it says, what do you want to name your section? Well, let's just call it beam, because why not? And again, we're not going to touch any of these. We're going to keep it solid, and we're going to keep it homogeneous. We go continue, and it says, all right, well, which material do you want associated with the section? Well, we only defined one material, which is elastic, so we're just going to stick with that. And again, this plane stress / strain thickness, this is the thickness of our beam into the page. Therefore, I'm going to check that because we know it's 1 meter. So since I'm doing everything in millimeters, I need to kind of add the extra zeros to say, all right, this is 1,000 millimeters into the page. So now I go OK. I have my nice beam section, and I can go OK. And if we did it correctly, we know that our shape will change colors to this bluey green color. As you guys remember, I kind of struggled with defining this color in the last slide quite a bit. All right, so now that we're done the properties, we can go on to the next one, which is the assembly. So again, when we're creating parts, those are just like creating the little Lego pieces. That's not actually creating the model itself. We do that over here in the assembly tab. So if we look at our assembly tab right now, it is empty. And this is kind of the workspace that's actually going to be analyzed when we run the model. So if I were to just click run right now, well, we're effectively analyzing nothing. So what we have to do is we have to bring our parts in and assemble the model. But luckily for us, our model is just one part, which is the beam. So therefore the assembly is actually rather simple. So what I'm going to do is I'm going to come over here to create instance, or if you guys want to go to the model tree, we have an assembly tab that we can expand, and we have instances. All you have to do is double click that, and it says, all right, well, which parts do you want to bring into your model? Well, we only have the one part right here, which is the beam. So we have our beam here. We can go okay. And now our beam is actually into the model space. So now our beam can actually be analyzed. And since we only have the one part, our assembly is actually now done. Therefore, I can close the assembly tree and we can move on to the next module. So we click here, we go, all right, the next one, of course, is step. So again, steps over here, these are the sequence of events that we want to do to our beam. So luckily for us, we only have one sequence of events, which is load the beam with that load. So I can double click step. What do I want to call this step? Well, I know I want to apply the load. So I'm just going to go apply load, and it's going to ask you for the different type of features you want for your step. So of course, we are just going to go with the default static general. You guys don't really know any of the other features. So again, a rule of thumb, if you don't know it, probably don't touch it. So we're going to go static general, continue. And the only thing that we're going to want to change, of course, is this nonlinear geometry. And this is because we are dealing with a linear elastic isotropic model under some pretty reasonable loading. So we actually won't have that many convergence issues. Now, once our model gets a lot more complex, we're going to start talking about this incrementation. This is going to be something very important and something that you guys will be using in your assignment. So don't worry. I know some of you guys in the last video might say, Clayton, you didn't cover incrementation. But yeah, I'm not going to cover it here either because we're not going to have any problems. But in later videos, I will show you guys what exactly this incrementation means. But for us in these type of simple models, it doesn't really matter. So we're just going to click on the nonlinear geometry, keep everything else the exact same, and go continue. So now we have two steps. Our first one's our initial step, which is not even really a step. It's just the beam how it initially is before any deformations or loads. And then we move on to our second step, which is when we actually apply those loads. So now that our step is done, we say, all right, go down here, interaction. Well, we don't have any interaction. So again, interaction is something that we do if we have multiple pieces in our model and we want to connect them, either like a glue perhaps, or maybe just adding some friction into the model. But we're not doing that in this particular case. So we can skip interaction and go down to loads. So the load module, we define two things in this. One is the actual loads on the model, and the second one are the boundary conditions. So what I'm going to do is I'm actually going to scroll down here so you guys can see. We have two options. The first one in our model tree is loads, and then the second one is boundary conditions. Now, if I want to, I can go up to the buttons on the side here because they feature the same thing. I see I have a create load button, and then down below I have a create boundary condition. So I need to create one of each, and it doesn't matter which order you guys do them in. So if I want to, let's say we want to do our load first, it's going to ask you what step you want to put the load in. Well, of course, we only have that one step, which is applying the load. So therefore, all I have to do is name my load. So what I'm going to do is I'm going to call it point load, because why not? That's basically what it is. I don't need to specify too much further. And the type of load, well, we know that this is simply just a concentrated force, so I don't need to go into much more detail after that. So I'm going to click continue, and it's going to say, all right, where in the model do you want to apply this load? Well, we know it's going to be at this corner over on the side here, so I'm going to go over the corner. As you guys can see, it can kind of highlights. I'm going to click it, and it'll remain highlighted, so I'm going to say, all right, this is great. Select the points that I want to. Well, I already did, so I can click done down here. And then it's going to ask for the magnitude of this load. The first one's saying, all right, what's the magnitude of the load in the horizontal direction or the X direction? So as we can see, we have a little X down here. Well, we know that this is actually a vertical load, so there's going to be nothing in the horizontal. And then, of course, the second thing is how much vertical load you want to apply. So I know I want 200 kilonewtons, but of course, I'm keeping everything in MPa, millimeters, and newtons. So this would be the equivalent of 200,000 newtons. And again, our load is pointing down, so we're actually going to have to add the negative sign in there to make sure it knows the direction of this load. So once I go OK, we can see over here that we actually have the load shown on the beam. So if you guys make a mistake, it'll actually be very apparent if you guys did, because it actually shows you what you applied to the beam. Luckily for us, that's exactly what we wanted to apply, so we're good to go for our loads. Next thing is going to be the boundary condition. So I come over here and say, all right, I got this BC. That basically means boundary condition. I can double click it. It'll bring me to my menu, and it's going to ask for the boundary conditions of the beam. Now, if you guys have boundary conditions on the beam that stay that way throughout the entire time, as well as are there initially, I recommend putting them in the initial step over here. And then all we have to do is state what the name of our boundary condition is. Well, we know that we are adding a fixed end. So I'm just going to type in fixed end. And then, of course, it's going to ask you, well, what type of boundary condition do you want to add? And we are going to add a displacement/rotation boundary condition. So I'm going to go continue. It's going to boot me out here, which says, all right, where in the model do you want to apply this? Well, we know that we want it on this surface over here, so I'm going to click it. It's going to remain highlighted, and I can go done. And then it's going to ask, all right, what do you want to restrict? Well, I want to restrict everything in the lateral direction. I want to restrict everything in the vertical direction. And then again, this rotation option we don't really need unless you guys are using shell elements. So I should have specified that in the last video. If you guys are using shell elements, you guys will have to specify a rotation degree of freedom. But as you guys remember, once we defined a section, we kept it solid. And since it's solid, we actually don't have a rotation degree of freedom. We only have translation degrees of freedom. So therefore, I only need to click these two. Now, let's say that you forget everything I just said and you click this on. It doesn't matter. ABAQUS will know that we actually don't have any rotations. So once you get, or rotational degree of freedoms, I should say. So once you guys run the model, ABAQUS will give you a warning saying that you guys don't need this, but it'll still carry out the analysis just fine. However, I don't like warnings, so I'm just going to get rid of that. I'm going to restrict the rotation, the displacement in both the horizontal and the vertical direction, and I'm just going to go OK. So we come over here, we see that we now have that nice fixed end over here, and we know that we already applied our load. So therefore, our beam is now defined, our boundary conditions, our loads are now defined. In addition, we have assigned the material properties to this beam. But again, the next step is actually one of the most important. We need to define a mesh. And if you guys forgot what the mesh is, this is, of course, where we are doing all the calculations within this beam. Because when we mesh it, so I'm just going to mesh it really quick here. Oops. So you guys actually have to click part over here. You don't want to go assembly. You guys always want to go part. And we're just going to mesh it really quick just to show you guys what happens. What happens is we create something called nodes and elements. So if we look at this square here, this is called an element, and it's defined by 4 nodes, which are in each one of the corners. So the displacement calculations of this beam will be carried out at the nodes, and depending on those displacement calculations, the stresses and strains will be calculated inside of the element. So why is this important, Clayton? Well, because we are using this one element here to approximate this whole region, which can be a problem sometimes, because let's say I calculate the stress right in the center of this element. Well, since this element is so big, it's going to assume that that stress is the same throughout this entire region, which we know is actually incorrect. Of course, there's going to be a change in stress, whether I'm looking at the bottom of the beam compared to the top, or vice versa if I'm looking laterally. So one of the key things that we're going to have to keep in mind when we're doing these mesh calculations is we want a thinner mesh in order to obtain better accuracy. So right now, I just went with the default mesh that ABAQUS gave me. I'm looking at this and saying, you know what, this is a little bit big over here. Let's make it a little bit smaller. So we actually have 2 options. The first one is this seed part option. And what this does is it assigns an approximate global size to every edge of our beam. So what it does is says 180, therefore it spaced these 2 points about 180 across and then 180 over here. And I say, you know what, maybe 180 is a little bit too big. Let's go 25. So now when I go 25, I click OK. It's going to say, well, you already created a mesh. Are you sure you want to delete it? Well, yes, I do, because I want to make it a little bit smaller. So now we can see that our element spacing will actually be a lot more thin now. So if I were to go mesh the part now, as we can see, it got much smaller. Now, this isn't the only option. Again, this right here applies that approximation to every surface within this model or every edge. But if I want to, I can define each surface separately. So what I do is I can go over here instead of seed part, I can go to seed edges, and I say, all right, well, this edge right here, you know what, 25 is a little bit too small. So let me select the two vertical edges. I can click OK. And then over here, we get a menu that says, well, what do you want to make these ones? Well, let's say that I want to make them a little bit bigger and I go 50. So now I go, okay, I'm going to apply that, go done. And since I modified the seeds, of course, my mesh gets deleted. So I'm going to have to redo the mesh. And now as we can see, our mesh along the top horizontal edge here is much thinner than it is along the vertical edge. So this is something that you guys can do if you want to specify a very specific mesh in some areas, but not so specific in the others. But for this course and for you guys can just go seed part, just pick an approximate size that's pretty small. We'll go 25. We'll apply it everywhere, and then we'll mesh the part, make it a little bit smaller. And actually, I need to actually do it over here. So let me just fix this really quick. I'll put this all back at 25 and we are good to go. So I'm going to mesh the part and I have my beam. Now, something that we kind of discussed at the end of last video is we can also change the element type. So again, these elements, these are where all of our calculations are going on. And depending on how much computation time and how much computation power we have, we can actually change the type of the elements to make them more exact. How do we do this? Well, there's a button right here that says S4R, and you guys may be confused what S4R is. It's actually one of the mini element types, but we can click it, and then we get this big menu over here with lots of different options. So one of the things we can do is we can specify different types of elements. So right now we can see by default we are using plane stress, but if I want to, I can click plane strain and use plane strain elements, but we're going to keep it plane stress. And the next thing we can do is define the geometric order. So right now we're at linear, meaning that all of our elements have those 4 nodes, one at each of the 4 corners. But if I want to, I can add more nodes by going quadratic. So this will go from 4 nodes, one at each corner, to 8 nodes, which will, again, help the accuracy because we're calculating the solution at more points, but it will cost increased computation power. Now, just like the step incrementation, you guys are running linear elastic models. Therefore, you guys actually don't need crazy elements, anything like that. So we're going to keep it linear. But one of the things that you guys can do to help increase the accuracy, if you guys want, is just click off this reduced integration. So the integration ABAQUS is done using a Gaussian scheme. What happens is we actually consider more points if we disable this reduced integration. So this will help our solution become more exact, or it'll help the accuracy of our solution. But of course, this will require more computation time. So I'm going to switch it off because these models are actually fairly quick. And now I actually defined the element type. So I have my beam, I have my I have all my loads, I have my boundary conditions, and I have my material properties. And now I actually have a mesh. So this mesh is actually kind of messy. There are ways that we can make this a lot nicer, but that's out of the scope of this course, so I'm just going to leave it as it is. And we're saying, all right, now that we have everything defined, we can actually run this analysis. So we come down to our module, and the running the analysis module is actually called job. So we're going to go down here to job, or we can come down here in the model tree, and it's going to say, all right, well, you actually have no jobs to do, so how can we run anything? So in order to create a job, we can either click the button over here for create the job, or we can go down here and double click jobs. It's going to say, oh, you want to create a job, give it a name. Well, we'll just simply call this analysis because a basic name for a basic beam. We can go continue. And again, in this job menu here, you don't really want to touch anything. The only thing that this really talks about is where do you want to store the files? Do you guys want to use multiple processors, GPU acceleration, stuff like that. So this is actually, if you guys have a nice video card, if you guys have multiple processors, we can actually boot this up. So I'll go 10 because why not? For these type of models, it's not going to make a difference, so don't worry about it too much at all. So now that once we have our job created, all we have to do is click on our job, right click it, and go submit right here. So what this is doing, this is taking everything in our assembly option, which we have over here. It takes all of our loads that we defined on this beam, as well as boundary conditions, in addition to our mesh, and then runs the analysis. So I'm going to right click it down here. I'm going to go submit. And it's going to do a couple things, of course. The first one is it's going to say submitted, which basically takes everything in the model space and converts it into a file. Now, this file is then going to be ran through the ABAQUS solver, which then will be shown by this running right here. After the analysis is complete, it's going to switch to complete, and therefore we can view our answers. So I'm going to right click it over here, and I'm going to go results. So here's our beam in the undeformed shape. If I want to see the deformed shape, I can come over here to plot deformed shape. As we can see, it bends down a little bit. I can play around, make it look a little bit funny. But if I want to analyze all of those stresses, as well as all the strains, everything like that, I can plot the contour shape over here. Now, I tried to make the legend a little bit bigger, but it appears I made it a little bit too big, so expect a different legend yet again for the third example. But again, looking at the stresses, it's kind of something that we'd expect. One of the big things that's a little bit different is we have a lot of stress accumulation around the holes, and this is something that you guys will see in your guys' assignment too. So in your assignment, you're going to be analyzing a masonry wall with a hole in the center. You guys will see a lot of stress concentrations around that hole. But one thing that we're actually going to compare right now is this vertical deflection at the end of the beam. So in order to switch from stresses to deflection, I can click S, which means stresses, go down to U, which is my deflections. And again, I don't want the magnitude, I want the vertical stress, so I'm going to go down to U2. So I'm going to click U2 over here, and as we can see, our U2 is around 20.8 millimeters over here. So this is going to be our deflection at the end over here, about 20.84 millimeters. All right, guys, so that's it for this tutorial. It's again short tutorial. The rest are going to be short. We're just showing you guys how to create these models and not really do too many crazy things with them. That's for graduate school if you guys want to if you guys want to join graduate school. So thank you guys all so much for listening. I really appreciate it. I will see you guys in example number 3.